Good morning, everybody, and thanks for viewing our webinar. Today, we'd like to go over an introduction to electron beam curing for coatings and inks, talk a little bit about what energy curable coatings are in general, maybe start with energy cure by ultraviolet, since people may be more familiar with that, and then talk to energy curing by electron beam. Talk about how you can control EB curing with the voltage and amperage in the electron beam instrument, a little bit about the equipment, and then end up with some common applications for electron beam curing and some a little bit on some of the equipment that people have out there. So next slide. And we're not sure how quickly the slides are going to appear, so I'm going to pause for a few seconds before I start talking about each slide, just to make sure everybody's caught up. If we look at what energy curable coatings are in general, they're formulated products that use a particular form of energy to initiate the conversion of a liquid coating into a cured solid film. And we can break this into two types. One which uses ultraviolet energy, possibly some visible light, and another which uses high energy electrons or electron beam curing, and that's what we're going to talk about today. So I mentioned we're going to start with a little bit on ultraviolet curing. And when we say UV curing, we're talking about using UV energy or visible light to cure our films. This is opposed to using heat or solvent evaporation or oxidation, otherwise known as air drying, to convert your liquid film into a solid coating. And to do that, we use energy of the electromagnetic spectrum between, say, 200 and 400 nanometers, maybe into the visible up to 450 nanometers, as indicated by the red circle on the chart on the left. And there's a lot of advantages to going to UV curable systems. The biggest one is productivity. That's why it's repeated 3 times there. If you're unaware of UV curing or energy curing in general, this is an incredibly fast process. It takes seconds, possibly fractions of a second, to cure the coating. This is in opposition to minutes or hours, which you might run into in thermal cure or air dry cure. So it's extremely fast and really improves your productivity. There are also 100 solids coatings, and this, combined with the ability to recycle unused coating and the overall cure speed, often leads to a lower overall cost per cured part. There's single component formulations, which eliminates errors that can be due to mixing in 2-component systems. They're 100 solid systems, so you don't have the VOC emission concerns, so you avoid some of the regulatory constraints. They're smaller than a large oven, and depending on what the energy costs in your area are, sometimes energy curing can be less expensive than other types of cure technology. Next. So if we look at energy cure by electron beam, we're using high energy electrons, and the energy is much higher with these electrons than the energy of the photons in UV curing. The advantages are mostly the same. It's a very fast cure process, so productivity is high. A lot of the same benefits as with UV curing, but there's an important distinction in that the cure is not impeded by pigments or other fillers. With UV, it's sometimes difficult to cure highly filled systems. Not so with electron beam. You can cure pigmented coatings or inks, or cure filled systems and get good through cure and adhesion easily with electron beam, where you'd have a challenge with UV. And just another way of looking at the energy differences, you can see that the UV energy again is in the UV tending into a little bit into the visible light, that energy is not strong enough to directly polymerize the oligomers and monomers that are used in energy curable coatings. So you have to use a photoinitiator. In contrast to that, the energy with electron beam curing is high enough to initiate polymerization all by itself. It ionizes organic materials, and so photoinitiators are not required. This is a big benefit. Scott mentioned that right now a lot of photoinitiators are in tight supply. They're difficult to get, so if you can cure your coatings without worrying about photoinitiators, that's a big plus. There's a few other factors. Photoinitiators are often the most expensive part of a formulation, so you can sometimes decrease your formulation cost by moving to electron beam. And finally, the photoinitiator fragments form a large part of the extractables that can be found in energy curable coatings. So if you're in flexible packaging, for example, and you're concerned about extractables, moving to electron beam can often reduce the extractable content of your coating. So we start to look at comparisons between UV and EB. Again, ultraviolet cure uses photons, electron beam uses accelerated electrons. With UV, the energy is determined by the wavelength of the energy that you're using, whereas electron beam, the energy of the electrons is determined by the accelerated voltage in the EB equipment. Typically somewhere 80, 180 kilovolts, maybe a little higher. If you want to look at how they compare on an energy unit conversion basis, a 350 nanometer photon has about 3.5 electron volts of energy, whereas electron beam is a lot higher. However, if you look at the total energy applied in a say a 50 gram per square meter layer of coating, the two processes come out to about the same total applied energy. UV works well with rigid and flexible substrates because of the shielding that's necessary for electron beam equipment. It's a lot easier to use flexible substrates, so they're preferred. Some of the challenges in 100 solids UV curable systems include the fact that it's a line of sight curing. If the area is not exposed to UV energy, then it's not going to cure. 100 solids energy curable systems have shrinkage associated with them. A good formulator knows how to accommodate that and work around that. And with UV, you get competing absorbance from different parts of the coating, especially pigments. With electron beam, some of the challenges are the same. You'll still get shrinkage. It's not really as big a deal for line of sight because electron beam does penetrate through many pigments and substrates, so that is not a big a deal for electron beam curing. But there is a higher capital cost when you install electron beam, and part of that is the need for shielding. So there are some pluses and minuses to both technologies. One of the key aspects of energy curing is how to cure down through the entire thickness of the coating or ink. This isn't such a big problem with heat-cured substrates because eventually, when you put something in an oven, everything will get hot. But depending on the materials in your formulation, everything may or may not see sufficient energy to cure. So if we look at the differences between ultraviolet and electron beam curing from the depth of cure perspective, the depth of cure in UV coatings, UV curing depends on the optical density of the material, whereas in electron beam it depends more on the mass density of material. UV depends on the peak irradiance, the power and the focus of the UV source, where electron beam, this is controlled by the accelerated potential or voltage of the electron beam. UV is really good for clear materials and somewhat limited in pigment-filled or opaque materials. Doesn't mean they can't be cured, but depending on what those pigments or opaque materials are, it can be extremely challenging. Whereas electron beam easily penetrates into clear materials, highly pigmented, filled, and opaque materials. And the two drawings below try to depict that. The one on the left shows that light is attenuated as it passes down through the thickness of coating, especially if there are pigments or fillers, whereas the high energy electrons will penetrate through the entire thickness of the coating, curing it all the way down to the substrate. So UV is effective for thick coatings with low pigment content. Electron beam is effective for thick or heavily pigmented filled coatings. And if you're into the adhesives and you're doing laminated adhesives with UV, you can cure if those materials are clear. But electron beam can cure even if the lamination is done using opaque materials. And this chart just shows an idea of how thick a coating you can penetrate depending on the voltage of the electron beam machine. So curing 15, 20 mils is not really an issue using EB. Not that you're going to have a 15 mil coating, but you may have some kind of lamination that's going to have a total thickness of that 15 or 20 mils. And that can be done using electron beam, whereas UV is going to be much more of a challenge. And again, if you're familiar with UV, then you'll recognize the setup on the left. This is a cross-section of a UV bulb and lamp system. The center is the UV bulb. This is usually a glass-filled or a glass bulb with some mercury vapor in it. At high temperatures, that mercury vapor will give off UV energy. It also gives off visible light and heat, roughly 30% of each, 33% of each. A lot of the light is reflected onto the part, and depending on what shape reflector you use, you can either get a very focused amount of UV using an elliptical reflector, or more of a flood effect using a parabolic reflector. In contrast, the electron beam source is usually a filament of metal that's heated, and electrons are extracted from the filament and accelerated towards the substrate using a voltage drop. They pass through a thin metallic foil window and then strike your coating, which then cures. Because some electrons may pass through the substrate and coating in other materials, which is a process which can create some high energy radiation, shielding is required to block this radiation and protect workers. So we've mentioned shielding a couple times with electron beam. It is a factor when you choose this technology. One of the nice things about electron beam is that you can easily control both the cure and depth of cure independent of each other. The applicator, or the person running the equipment, can control both dose and voltage. The dose refers to the quantity of electrons impacting the surface, and that again goes to cure speed and cross-link density. Their dose will not penetrate any deeper, but it will cause higher cross-link density at the surface of the film and higher cure speed. By changing the voltage, you can determine how fast the electrons are traveling the impact and how deeply they will penetrate into your coating. So you can use a higher voltage to deliver a constant dose. You won't change the cross-link density, but you will increase the depth of cure. So you have two factors which can be controlled independently of each other to get a precise degree of cure on your coating. So we've talked about some of the benefits of electron beam curing. It's a very fast process. That means high throughput. It can penetrate into and through the coating or ink and through some substrates, meaning it's good for laminating. It's good for curing pigmented systems. You're going to get good through curing good adhesion. There's not a lot of heat generated, which means that heat-sensitive substrates can be used, which isn't always the case with UV. The energy can be precisely controlled, which means you have a lot of control over the cure of your system, which is always a good thing to have. And again, these systems are generally 100% solids, so they have low to no VOCs. So with those benefits, some of the things you might want to consider when trying to see if electron beam is a good fit for your operation is the benefits of electron beam may allow you to penetrate into new markets. If you're just strictly using UV right now, you may not be able to use highly pigmented systems, or you may not be able to get into lamination, which electron beam will allow you to do. On the other side, there's the capital cost, which is going to be high at the beginning, but I will say that the electron beam manufacturers have done a nice job in reducing the cost of their equipment over the last few years. Operating costs will decrease as you see the benefits of fast throughput and low maintenance. As far as end-use properties goes, here's where it gets a little bit more granular. The end-use property is going to be really specific to the formulation and your end use. But some of the things that you can expect using electron beam are better surface cure, so a harder, more scratch and abrasion resistant surface. And if that's something that can allow you to expand your market, that's a benefit. There's fitness for flexible packaging because we mentioned before, electron does not use any photoinitiators. Coatings will have fewer extractables, which is a big plus if you're going to be in the flexible packaging market. And again, because of the low heat, you might be able to use substrates which before were out of reach because of heat sensitivity.
So a little bit on the on what the electron beam applications are. If you talk to the suppliers, ESI or Comet, E-beam Technologies or others, one of the focus areas for them right now is, aside from the fact that you can use electron beam to cure coatings, inks, and adhesives, you can also use it to modify the surface of a substrate directly. And that's the biggest area for them, although perhaps not the biggest growth area for them. Right now, what we're hearing is the packaging, especially food packaging area, for coatings, inks, and adhesives is actually one of the biggest areas of growth. But as I say, there's a lot of applications for electron beam, even beyond using a rod cure chemistry.
So if we look at some of the common applications, especially maybe not just for the graphics, but foils and paper upgrade, there's a lot of interest now in producing paper upgrade that contains a very fine print for wood finishes that will be laminated onto PVC substrates or other substrates and give a real lifelike look to them. Because these are pigmented, electron beam is often a great tool to use to cure these materials. Tapes, building panels, we've seen pattern sheets where you have a pattern on a film that could be transferred to the surface of your coating, and you can cure through that film with electron beam, whereas you might not be able to do the same with UV. This also, electron beam is also finding inroads in in-mold labeling, laminated adhesives, as we've mentioned 2 or 3 times already, auto interior coatings, and its electron beams has been looked at for quite a while now in coil coatings.
Just a reminder to everybody, hopefully you received an email with this presentation so you can follow along that way if it's not displaying on your computer. Plus, we're also recording this webinar, and we will send you a link at the end. So from a just common applications, these are all examples. You see a pouch, you see the candy, you see the powder pouches as well, the foil. All of these are examples of customers that have used E-beam curing for their inks and coatings and adhesives, and use them very well. As I said, I think there's a big push into the food packaging market for E-beam right now, and that goes across flexo, litho, and inkjet platforms. So if you look at, for instance, Comexi central impression press, the offset press, globally there's about 15 that have already been installed, but they have between 5 and 10 more they're expecting to install each and every year. And the HP Indigo, these inks have a bit of wax in them. They're not heat sealable, so they need a way of protecting the ink or the finish. So there's an opportunity there in the HP Indigo space for E-beam cured OPVs because of the lack of heat that's generated. Uteco has come up with a couple of different printers that are using E-beam. They have a Gaia inkjet printer that they introduced at Label Expo a couple of years ago. It had some issues with odor and cure speed and resolution, which they seem to have improved upon with their latest or second version of the Gaia Uteco inkjet press. So they started around 25 meters a minute with some odor and cure issues and resolution issues. They went with better inkjet heads, and now they're getting 90 meters a minute out of the press. And the flexo area, a lot of E-beam flexo inks again have improved. This is with the flexo press, the E-beam is at the end of the press, and as you know, you have several colors to go through, so it's a wet on wet kind of process, which can produce some issues if you don't know what you're doing with the inks. But recently, people have overcome those issues. There's several now really interesting technologies that allow you to do wet on wet printing without getting the muddled effect from mixing the ink, the wet inks. And that's worked out pretty well.
And lastly, just want to leave you this more as reference. These are common terminology for describing the energy used in electron beam curing. We mentioned voltage, that's related to the electron penetration. The units are usually in electron volts, either mega electron volts or kilo electron volts. Amperage has to do with the beam current. Kilowatts is just the total energy used. Dose technically refers to the absorbed energy, not necessarily the energy that's being put out by the machine, but the energy that's absorbed by your coating and the substrate. And this is expressed in kilograys or megarads, and the relationship between those two is shown there. And finally, the dose rate, or the energy being applied to your coating with time. is in the kilograde per second would be the unit. So this is just more of a reference. If you are going to get into electron beam, these are the terms that describe the energy used when using electron beam curing technology. So in summary, electron beam curing is another way to deliver energy to a coating to effect cure. It's similar to UV curing, but in that they're both energy curing technologies, but electron beam has its own advantages. The main one being its ability to penetrate into pigmented and thick coatings. Electron beam allows for faster cure versus a lot of different technologies. This results in increased throughput for your coating process. Electron beam has generally reduced extractables compared to UV coatings, which is beneficial in a lot of markets currently. And because, again, you're getting rid of photoinitiators, you can often see formulation cost improvements when switching to electron beam coatings. That's it. With that, thanks for watching.
Yeah, I think we'd like to open up the questions. As you know, all your microphones are muted, so you can hear us. But that is a misfortune. The only way you can ask a question is by using the instant messenger. You'll see in the bottom left, you'll see a sort of shout out, and you can ask your question at the bottom there. And I'll start, actually. I think I'll see if I can stump John with some questions. The first question I had that I get a lot, actually, lately, is this trend towards soft touch. Would electron beam be any better than UV curing for soft touch coatings?
It could quite possibly be better. Most soft touch formulations that I'm familiar with require the addition of some kind of particle, either organic or inorganic. And if the particles that you're using to generate that haptic feel have a strong absorbance in the UV, then electron beam would certainly be a better choice of cure technology than UV would.
In terms of, the first question we got was what percentage of companies are using electron beam? And I'll probably take that one. I guess it's if you talk to the electron beam manufacturers, they'll tell you that it's gaining ground, but it sort of depends upon the platform. Right now, for instance, there is electron beam. There are companies that are using electron beam for inkjet, but there are very few. And some companies are using it for flexo, and a large interest from Pepsi to try that, using a 7-8 color press, flexo press, going 400 meters a minute to produce, bags, snack bags, that kind of thing. I would say overall, though, the market globally is probably about 5% and 5 to 7% electron beam. How is the chemistry affecting the cure speed?
In general, the chemistry of any energy curable system, whether it's electron beam or UV, is most generally related to the acrylate equivalent weight of the system. In other words, the number of double bonds per weight. So with any system, if you put higher functionality materials in there, you can increase the cure speed. If you have monofunction materials, your cure speed is going to be a lot slower. So it mostly has to do with the functionality and the equivalent weight of your system. Things with higher functionality would cure faster than lower functionality. And
I think, adding to that question, I like this question about, contrary to UV and EB, is not selective. How damaging is EB to the substrate, and are certain chemistries more sensitive than others? And I mean, part of the answer to that question is yes, it can be damaging to the substrate, but you do have a lot of control over the depth and the energy that you use.
Yeah, it's one of the nice things about EB is how precisely you can control the amount of energy, the amount of electrons and the energy of electrons that are impinging your coating, so that you can limit the penetration of the electrons to the coating and not so much into the substrate.
And that's true across the web. It's probably more in terms of regular UV versus EB. Electron beam tends to be more constant across even up to a 6-7 foot wide web.
And also just something to note, because electron beam is a lot, or UV puts out a lot of heat energy. You eliminate some substrates right away because of their heat sensitivity, and you don't see that with electron beam. So there's a positive for electron beam there.
One of the, I don't want to paint too glowing a picture here. So I guess, John, I was wondering if maybe you could summarize a couple of the disadvantages of using electron beam.
Well, we mentioned just the cost and the shielding. That's something that's to be laid out at the beginning. And we didn't talk about it too much, but in order to prevent some of this high energy or contain it within the machine, you have the shielding, and then you also make sure that the substrates generally proceed through what's known as a tortuous pass through the machine. So it's not a straight line through the machine. That's why flexible substrates are preferred. And that means there's no direct line of sight for the energy to leave the machine. And what this means is that things like continuous web operations are much more preferred. Something like a sheet fed operation is extremely difficult to do with electron beam. So that would be another disadvantage for electron beam.
Yeah, and the question I think has kind of been answered, but maybe you asked it in a different way. Is there any inherent advantage to E-beam over UV in terms of bond strength to a superimposed heat-pressed laminate film, such as plastic card printing? I see inherent advantages for it, in period, for lamination, but just from a control point of view.
Yeah, from a control point of view, I always look at these things and think, well, if you're really good at something. So yes, because I think the advantage again would be time in terms of getting the energy through the materials to the layers that you're trying to cure. In the EB technology is going to be a lot faster than in a heat press laminate film. It's going to take a little bit longer for that heat to get to the curing layers and to affect cure than if you use electron beam. So I think the advantage there is in time, maybe not just strict bond strength.
The next question was something I've been asked a couple of times in a couple of different ways. It really relates to how is there an actual difference or a curing difference between types of oligomers or monomers with E-beam curing? And the way he stated it here is E-beam is here to initiate the reaction through radical creation. I'm surprised only the monomer functionality controls the speed.
Well, it's maybe a little bit different than your earlier question. So, yeah, I was assuming for a given dose and voltage drop, what will control the cure speed is the functionality, the acrylated equivalent weight. However, with electron beam, because you can control the number of electrons and how deeply they penetrate, you can increase cure speed by increasing your dose as well. That's certainly true. So it's not just the functionality of the oligomers and monomers that affect cure speed, but the amount of energy in the form of the electrons that you're putting into your film is going to affect your cure speed as well.
And one of the earlier questions about the market and where it's headed, I should mention that a number of suppliers of printers are now going to be, including Uteco and Bobst, are going to have EB flexo printers at Drupa 2020, and we see that as a trend. So EB flexo into packaging seems to be a definite trend with some major players entering the market. So if there are no more questions, I think someone's typing a question. As I said earlier, this presentation is being recorded, and we can send out it out. Just send a message to replying to the invitation you got. If you didn't get the file, we can also provide you with the file with the presentation itself. So the last question: LED light sources have higher and higher outputs. Does E-beam still have an advantage when it comes to through cure over LED, UV LED?
Yeah, I think it still does. You're correct. The LED light manufacturers have done a really good job increasing the output of their lamps. Especially the longer wavelength lamps, which are going to penetrate deeper. You're still going to have the same issues, though, if the LED energy, and if there's something in your formulation that absorbs in the same area that the LED lamp is putting out its energy, that's going to attenuate the LED irradiation as well. And that's not going to happen with an electron beam unit. So I think from a cure depth standpoint, electron beam is always going to have an advantage when you're talking about filled and pigmented systems.
Although UV LED does have an advantage over traditional UV. The disadvantage to UV LED is more with surface cure. All right, I appreciate everybody spending their Friday morning with us talking about electron beam. I hope you learned something. And if you have any further questions, please feel free to drop us a line. All right, thanks everyone.